Okay, so welcome to this video. In this video, what we're going to talk about is voltage-gated ion channels. Okay, so ion channels that can be opened by depolarizing the electrical potential difference across the cell membrane. Okay. So, for short, voltage-gated ion channels can be abbreviated down to VGICs. Okay, V for voltage, G for gated, I for ion, and then C for channels. Okay, and we'll be using that abbreviation often in this video. Okay, right, so let me start off by discussing the overall outline for this video then. Okay, so we're going to start off by a basic discussion of the action potential, okay, and this will motivate our more in-depth discussion later of the different types of voltage-gated ion channels, because by studying the action potential, we'll see the essential properties of the voltage-gated ion channels, which we're hoping to be able to explain. Okay, so for instance, we'll see that they open in response to depolarization of the electrical potential difference across the cell membrane. We'll also see that they're going to inactivate very quickly after opening, even though the electrical potential difference across the cell membrane is still depolarized. Both of these phenomena we are hoping to explain by discussing the structure and mechanisms of these things in more detail. Okay, then after we've discussed the action potential, what we'll go on to is this more in-depth study of the different types of voltage-gated ion channels. Okay, so we'll talk about the voltage-gated potassium channels first, because they are the ones that are best understood. We have crystal structures for the voltage-gated potassium channels, so they are very well understood. So we'll talk about, for instance, their structure first. Then we'll talk about the gating mechanism, so how depolarization can open the voltage-gated ion channel, the voltage-gated potassium channel. Then what we'll talk about is how potassium ions actually move through the voltage-gated potassium channel, so the mechanism of permeation. We'll talk about how voltage-gated potassium channels select for potassium ions specifically. Okay. Then what we'll talk about is the mechanisms of inactivation, and there are two different known mechanisms of inactivation called fast inactivation, also called N-type inactivation, and slow inactivation, also called C-type inactivation, and we'll discuss both of those mechanisms. Okay, then what we'll do is we'll move on to other types of voltage-gated ion channels. So firstly, we'll move on to the calcium-activated potassium channels. And you might think, well, what are the calcium-activated potassium channels doing in the video on voltage-gated ion channels? Well, the answer is the calcium-activated potassium channels have a very similar structure to the voltage-gated potassium channels, and indeed some of them are voltage-activated. Okay, so there's one good reason to put them in with the other voltage-gated ion channels. Another reason for putting the the calcium-gated potassium channels in this discussion of voltage-gated ion channels is that the calcium-activated potassium channels actually play an extremely important role in the action potential. Okay, so there's another good reason that we will study those. They are important in the after hyperpolarization, which we'll discuss when we have our initial discussion of the action potential. Then, after we've discussed the calcium-activated potassium channels, we'll move on to voltage-gated sodium channels, and then finally we'll talk about voltage-gated calcium channels. So that now is the structure then for this video. Okay, so we're going to start off then with a basic discussion of action potentials. So this is where we're going to start by discussing action potentials. So action potentials are these electrical signals that can propagate along certain excitable cells. Okay, principal example being nervous tissue and also muscle tissue. Okay, we will throughout this video really be dwelling most on neurons. Okay, so what I firstly then want to start off with is a discussion of the fact that there is a resting electrical potential difference across the cell membrane of not just neurons but all cells in the body, but we're interested in neurons, so we'll use the example of neurons. So we'll talk about the resting electrical potential difference across the cell membrane of the neurons. Okay, then we'll talk about the resting concentration gradients of ions across the cell membrane of neurons. Okay, and then what we'll talk about is, we'll start with what actually causes a neuron to fire an action potential, and then we'll actually discuss the initiation of an action potential, the propagation of an action potential by saltatory conduction, and we'll see where voltage-gated ion channels are extremely important in all of this. Okay, right, so let me start by drawing then a little picture of a neuron. Okay, so neurons obviously all look different. There are loads of different types of neurons. However, I will draw the most archetypal picture of a neuron you can have, okay, which is this picture where you have the cell body of the neuron, the soma of the neuron here, okay, with lots of these dendrites, okay, these processes coming off the cell body of the neuron, and then you have one axon, this other type of process coming off the cell body of the neuron here, okay, and then it will have an axon terminal right at the end there. Okay, so I'll now put a nucleus in the cell body of our neuron here. Okay, so there's a basic picture of a neuron. Okay, so let's start off then with this discussion of the electrical potential difference across the cell membrane of a neuron. Okay, so basically electrical potential is this concept from theoretical physics. Okay, it is a mathematical model to explain the reality that we live in. Okay, and the idea is this, that you give to every point in three-dimensional space a real number. Okay, this number can be positive, it can be negative, it can be zero, it can be an integer, it can be a rational, it can be an irrational, it can be whatever you like, as long as it's a real number. Okay, it can't be imaginary. Okay, so you have to stay within the set of real numbers, basically. Okay, now, the idea is this, because all of the points of the cytoplasm of the neuron are in electrical equilibrium with one another, all of the points in the cytoplasm of the neuron have the same electrical potential, basically. Okay, the number that is ascribed to all of the points inside the neuron is the same, basically. Okay, so what I mean by that is if I had a little man, okay, here is this little man, and he's got a machine for measuring electrical potential, okay, and I put this little man inside the cytoplasm of the cell, and I'll just colour in some of the cytoplasm of the cell in green here. Okay, so if I put this little man inside the cytoplasm of the cell, anywhere inside the cytoplasm of the cell, and he used this machine to measure the electrical potential of all of those different points inside the cytoplasm of the cell, he would get the same value, basically. Okay, we will call that value the electrical potential, capital E, okay, and then I'll subscript it I for the electrical potential intracellularly, and it's just some real number. Okay, so all of the points inside the cytoplasm of the cell have the same electrical potential, the electrical potential intracellularly. Okay, right. Now, similarly, all the points outside the cell, they all have the same electrical potential because they're all in electrical equilibrium with one another because, of course, they're in contact with one another. Okay, so all of the points outside of the cell, all of the extracellular fluid points here are in electrical equilibrium with one another, and the electrical potential of all of those points is the same. So if my little man went and stood in any of these red portions, basically, and measured the electrical potential there, he would get the same answer. Okay, and we'll call that number, that answer that he would get for the electrical potential anywhere in the extracellular fluid, we'll call it capital E for electrical potential, and then we'll subscript it E for extracellularly. Okay, so this stands for the electrical potential extracellularly. Okay, now, here comes the big thing. Okay, the electrical potential extracellularly and the electrical potential intracellularly are not the same thing, okay? Because the cytoplasm and the extracellular fluid are not in electrical equilibrium with one another. They have the cell membrane here splitting them apart, so they're not in electrical equilibrium with one another, okay? And the electrical potential extracellularly is not the same as the electrical potential intracellularly, at least not in the case of most cells, and not in the case of our neuron here. Okay, so instead, we can now come up with the concept of there being an electrical potential difference, or a voltage, across the cell membrane. Okay, so voltage is the more common term to see, but electrical potential difference tells it like it is, basically. Voltage just means an electrical potential difference, okay, and it means that if you go from the extracellular fluid to the intracellular fluid, your electrical potential will change. So when people talk about the membrane voltage, and they often denote it V subscript M like this, what this actually means is if I have my little man in the extracellular fluid, okay, and then moved him from the extracellular fluid to the intracellular fluid, how much would the number on his screen change? So he started off in the extracellular fluid, okay, and he was measuring electrical potential, and he measures this number here, the electrical potential extracellularly, okay. Then he has jumped across the cell membrane, and he's now in the intracellular fluid, and he's going to measure the electrical potential in the intracellular fluid, okay. Now he's got a new number on his screen, the electrical potential difference across the cell membrane, or the membrane voltage, is how much does that number change, and it's always from extracellular to intracellular, so it's never moving from intracellular to extracellular. We always take extracellular as the starting point. After all, the physiologist usually starts off outside the cell. Okay, right, so let's write out a formula then for the electrical potential difference across the cell membrane in terms of the electrical potentials extracellularly and the electrical potentials intracellularly. Okay, so we want to know how much does the electrical potential that is on the screen for the little man here actually change when he moves from extracellular to intracellular. Okay, right, so that's going to be the new value of electrical potential, the new value that's on his screen, okay, after he's made the jump, which is the electrical potential intracellularly, subtract the value that he had before, okay, which is the electrical potential extracellularly, okay, so that will tell us how much the electrical potential on his screen changes when he moves from extracellularly to intracellularly. The new value, okay, the electrical potential intracellularly minus the old value. That's how much you change basically when you move from extracellular to intracellular. Okay, so that is what is meant by the electrical potential difference across the cell membrane. It's how much would your electrical potential change if you move from extracellular to intracellular, basically. Okay, right. Now, this is usually a value of negative 65 millivolts. Okay, so before I can elaborate on that anymore, I need to tell you about the units that electrical potential is measured in. Okay, so we've discussed that electrical potential is this value that is ascribed to every point in three-dimensional space. Okay, now the units of electrical potential are the volt. Okay, so every point is given this real number, and then the unit is the volt, basically. Okay, and then if we're asking about an electrical potential difference between 2 points, then of course electrical potential difference is also going to be measured in volts, because all you're doing is taking one number, which is in the units of volts, and subtracting off another number. You're asking what's the difference between these two numbers, and of course when you do that, the units is still going to be volts. Okay, so the units of electrical potential difference, as well as the units of actual electrical potential itself, is also the volt. Okay, then what does milli mean? Okay, what does the little m here? Well, all that means is 1,000th of a volt. So really, all this means is that the electrical potential difference across the cell membrane is negative 0.065 volts. Okay, that's generally the resting electrical potential difference that you have across the cell membrane, basically. Okay, so what does that actually mean then? Well, that means that if the little man moves from extracellular to intracellular, the electrical potential, the number on his screen, goes down by 0.065 volts, basically. Okay, so that means that the electrical potential intracellularly is lower than the electrical potential extracellularly, and it's lower by 65 millivolts, basically. So we could show this quite simply on a graph like so. Okay, we could let this line here represent the electrical potential extracellularly. Okay, so I will colour that line in red here. Okay, and then we could let this line below here represent the electrical potential intracellularly. And basically the electrical potential intracellularly is clearly on this diagram lower than the electrical potential extracellularly. So basically when the little man moves from extracellular to intracellular, the electrical potential drops down by negative 65 millivolts. So this doesn't tell you what the level of the electrical potential extracellularly or the level of the electrical potential intracellularly is. Those numbers it doesn't tell you. All it tells you is what the jump down is from extracellular to intracellular. It tells you the electrical potential difference from extracellular to intracellular. Okay, so that's the concept of resting electrical potential difference. So the cell will have this electrical potential difference across its cell membrane at the resting state, basically. Okay, and we're not going to discuss how the resting electrical potential difference is actually established. That's through, of course, the leaky sodium and potassium channels and the gradients that you have of sodium and potassium across the cell membrane. Okay, but we're not going to go there because it's a long explanation. Okay. Right, what I do want to talk about, however, is the gradients that you do have of sodium, potassium. I also want to do calcium and chloride across the cell membrane. Okay, right, so we'll start off then with the gradients of sodium, potassium, calcium and chloride across the cell membrane, and then we'll move on to a discussion of how you can actually generate action potentials in the cell. Okay, right, so let me just put these numbers up here then. So let's say this is the cell membrane of our cell. Let's say this is the extracellular fluid side. Okay, so I'll colour the extracellular fluid side in red to match it with this picture. And this therefore is the cytoplasmic side. Okay, which I'll colour in green to match it with this picture. Okay, now what I want to tell you about is the gradients that you have for sodium, potassium, calcium and chloride across the cell membrane, because we're going to use these ionic gradients in order to explore the action potential, basically. Okay, right, so we'll start off with sodium, one of the most important. Okay, so sodium concentration extracellularly is around 145 millimolar, and I should stress that these numbers will differ depending on which source you go to, okay, but they'll all be around this, basically. Okay, so these numbers, if you go to another source, you'll find them slightly differently, but you'll notice that they're very close, okay? So take these as being around that level rather than exactly that level. Okay, so sodium concentration extracellularly then is around 145 millimolar, okay, and intracellularly it's around 12 millimolar. Okay, so this is sodium here. Okay. Right, now what should you take from that? Well, you should take the fact that the extracellular concentration of sodium is 12 times bigger than the intracellular concentration of sodium. Okay, so there's a 12-fold concentration gradient favouring the movement of sodium into the cell, basically. Okay, so that's the important thing. The absolute numbers, again, don't really matter that much. The relative size of the concentration extracellularly to the concentration intracellularly is what's important, the 12-fold gradient favouring the movement inwards. Okay, right. Now let me talk about the gradient then of potassium across the cell membrane. Now it's the opposite way round for potassium. Potassium concentration extracellularly is 4 millimolar or thereabouts, whilst the concentration of potassium intracellularly is more near 155 millimolar. Okay, so that's approaching a 40-fold gradient of potassium favouring its movement out of the cell, basically. Okay, so the concentration gradient of potassium is most definitely saying go out, basically. Okay, now let me talk about the calcium gradient across the cell membrane. Okay, so calcium's gradient is enormous, okay, compared to the sodium and potassium gradients, okay, and that's because calcium is actually quite a toxic ion to the cell, okay, and therefore the level inside the cytoplasm is kept very low under resting conditions. So extracellular calcium concentration is around 1.5 millimolar, but then intracellular calcium concentration is around 100 nanomolar. Okay, so remember, nano means 10 to the negative 9. Okay, so 1 billionth of a molar, basically, whereas milli means 1,000th of a molar. Okay, so that's a 15,000-fold gradient of calcium favouring its movement into the cytoplasm of the cell. So that's a very powerful concentration gradient across the cell membrane for calcium, basically. Okay, right, and the final one that I want to tell you about is chloride, but I'll have to put chloride down here, okay, since we've run out of space. So the chloride gradient across the cell membrane again favours its movement into the cytoplasm of the cell, usually. Okay, so the concentration of chloride in the extracellular fluid is usually around 110 millimolar. Okay, whilst the concentration of chloride in the intracellular fluid is usually more around 4 millimolar. Okay, so that's another close to 30-fold gradient of chloride favouring its movement into the cell. Okay, so again, chloride's gradient favours its movement into the cytoplasm of the cell. Okay, so we've now got all of the sort of prerequisite understanding that we need in order to discuss the generation and propagation of action potentials. Okay, we now understand what is meant by the electrical potential difference across the cell membrane. Okay, and we know the resting concentrations of ions across the cell membrane. Okay, right, so let me start off my discussion of the action potential by discussing the input that the neuron is receiving from loads of other neurons. Okay, so what actually makes a neuron fire an action potential? Well, it's the input that this neuron is getting from loads of other neurons. Okay, a neuron just doesn't fire an action potential in response to nothing. It's a signal that it sends when it has received enough activation. Okay, so what will happen is loads of other neurons are coming in and synapsing onto this neuron here, and those synapses will either be trying to excite the neuron here into firing an action potential, or they'll be trying to inhibit it from firing an action potential. Okay, so let me discuss this in a bit more detail. Okay, so I've drawn a very basic picture of a neuron here. Okay, I've shown the dendrites as these beautiful little smooth finger-like projections coming off the cell body. In reality, the dendrites are much more complicated than that. Dendrites in reality are absolutely covered in these little sort of mushroom-shaped projections coming off them. Okay, so this is the dendrite membrane here. Okay, so I'll colour in the dendrite membrane in green here. So this is this little section of membrane that's, say, removed from here. And basically, these dendrites are covered in these little mushroom-shaped projections coming off them here. Okay, and these little mushroom-shaped projections coming off the dendrite cell membrane are called dendritic spines. Okay, and these dendritic spines are the sites where other neurons can synapse onto this neuron, basically. So this is a dendritic spine. Okay, so what you're going to then have is the axon terminal of another neuron coming onto this dendritic spine here. Okay, so here is the axon terminal from some other neuron here. Okay, and we're assuming that this is a neuron in the brain, okay? So it's going to be stimulated by other neurons rather than by sensory stimuli or other such stimuli. Okay, right. So basically, this neuron here is going to have its dendrites covered in these dendritic spines, which are going to have other neurons sending their axon terminals onto these dendritic spines and therefore synapsing onto our neuron. Okay, so all the time this neuron is receiving this continuous input from its different synapses, basically, because if other neurons that are connected to this one fire an action potential, then their axon terminals will be releasing neurotransmitter onto the dendritic spine of this neuron, basically. Okay, and neurotransmitters at synapses can be either excitatory, they can either be trying to stimulate this neuron into firing an action potential, or they can be inhibitory, they can be trying to inhibit this neuron from firing an action potential. So basically this neuron will be getting lots of input from loads of different neurons, and at all of these different synapses on all of these different dendritic spines, you'll either be getting excitatory neurotransmitter released onto the dendritic spine or inhibitory neurotransmitter released onto the dendritic spine. Okay, an excitatory neurotransmitter is going to be trying to excite the neuron into firing an action potential, and inhibitory neurotransmitter is going to be trying to inhibit the neuron from firing an action potential. And the neuron will sum this all up, okay? It will look at all of the excitatory inputs that it's getting and all of the inhibitory inputs that it's getting and decide whether or not it wants to fire an action potential. Okay, so that's the basic picture of this. Now what's the actual reality of this? Okay, how does having excitatory neurotransmitter or inhibitory neurotransmitter released onto a dendritic spine actually affect the probability that this neuron is going to fire an action potential? Well, the first thing to tell you about is where neurons actually usually initiate action potentials. So basically, action potentials do not usually start in the dendrites. Okay, dendrites usually cannot fire action potentials. Action potentials usually actually begin in this first portion of the axon here. And this first special portion of the axon is what's called the axon hillock. Okay, so this is usually the first place that the action potential actually begins. Okay, right, so all of the input then that's coming into all of these dendritic spines over the dendrites is going to be causing some sort of effect at the axon hillock to either try and excite the axon hillock into generating an action potential or inhibit it from generating an action potential. So how do the dendritic spines communicate their input to the axon hillock? Okay, so let's now talk about the two major types of neurotransmitter that are used in the brain. Okay, so in the brain, the major excitatory neurotransmitter that is used is called glutamate. Okay, and this neurotransmitter will be released onto a dendritic spine by an axon terminal that is trying to excite this neuron here. So certain axon terminals, certain neurons that are connecting into this neuron will be trying to excite it, and their neurotransmitter will most likely be glutamate. Okay, the neurons which synapse onto this neuron and want to inhibit this neuron from firing an action potential, their neurotransmitter will most likely be GABA. GABA is the main inhibitory neurotransmitter within the brain. Okay, so different neurons will be using different neurotransmitters in their synapses onto this neuron, basically. Okay, and I want to stress that an axon terminal will only either be excitatory or inhibitory with regards to this neuron. It will only be releasing glutamate or GABA. It doesn't release both of them, okay, depending on what it feels like. Okay, so a neuron will either be exciting this neuron and therefore its axon terminal will be releasing glutamate onto a dendritic spine of this neuron, or it will be trying to inhibit this neuron, in which case its axon terminal will be releasing GABA onto the dendritic spine of this neuron. Okay, right. Now, glutamate and GABA, when they're released onto the dendritic spine, they will work on receptors in the membrane of the dendritic spine. So if I just now draw the dendritic spine out in more detail here, you will have receptors which are ion channels that are gated by ligand binding. Okay, and for short these are called ligand gated ion channels, or LGICs. Okay, so this is in full is ligand-gated ion channels. Now, of course, we are discussing voltage-gated ion channels, not ligand-gated ion channels, so we're not going to discuss these in detail, but understand that there are special ligand-gated ion channels for glutamate, called glutamate receptors, and then there are special ligand-gated ion channels for GABA, called GABA receptors. Okay, right. Now, the ligand-gated ion channels for glutamate and GABA differ in which ion they can allow through. Okay, so glutamate ligand-gated ion channels will open in response to glutamate binding to their extracellular domain. Okay, so glutamate molecules will bind to their extracellular portion. Okay, that will cause the glutamate ligand-gated ion channel to open, and then the glutamate ligand-gated ion channel will allow sodium ions into the cytoplasm of the cell. So it will conduct sodium ions into the cytoplasm of the cell if it's a glutamate ligand-gated ion channel. In contrast, GABA ligand-gated ion channels will open and allow in chloride anions into the cytoplasm of the cell rather than sodium ions. Okay, so not only is it a different ion, but it's an ion with a different charge. Okay, so glutamate, the main excitatory neurotransmitter, is going to be opening ligand-gated ion channels and allowing sodium ions to enter the cytoplasm of the cell. Okay, whereas GABA is going to be opening GABA ligand-gated ion channels, and when those open, they'll be allowing chloride anions into the cell. Now, understand why, when you open a ligand-gated ion channel, you're going to be getting these movements. Okay, so for instance, if you are a glutamate ligand-gated ion channel, then when you open, you're going to have a sodium channel now open in the cell membrane. Now, why does sodium then come into the cell rather than out of the cell? Well, the reason for that is that we've got this 12-fold concentration gradient of sodium favouring its movement into the cell. You've also got to consider the fact that we have this resting electrical potential difference across the cell membrane of negative 65 millivolts. That means the electrical potential intracellularly is lower than the electrical potential extracellularly by 65 millivolts. Sodium ions are a positively charged ion, and it's a basic law of physics that says that positively charged ions want to go where the electrical potential is lower, okay, which in this case is the intracellular compartment. So sodium ions also want to go into the intracellular compartment because the electrical potential is lower there. So both the concentration gradient and the electrical gradient across the cell membrane are saying to sodium ions, if you get a chance, go in, basically. And so when you open this glutamate ligand-gated ion channel, sodium goes in, basically. Okay? For chloride, it's a little bit more complicated. Okay, we know that there is this strong concentration gradient across the cell membrane of around 30-fold, favouring the movement of chloride into the cell. Okay, however, chloride is negatively charged, and negatively charged ions want to do the exact opposite to positively charged ions with regards to electrical potential. Positively charged ions wanted to go where the electrical potential is lowest. Chloride and indeed other negatively charged ions will want to go where the electrical potential is highest. So the electrical gradient in this case is saying to chloride anions, go out, basically. So the question is, who wins then? The concentration gradient says go in, the electrical gradient says go out, okay? Which is stronger? Well, in this case, this 30-fold concentration gradient of chloride is stronger than the electrical gradient, basically, so you still get chloride going in. Of course, the chloride movement in will be less because of the electrical gradient opposing the concentration gradient. So if you didn't have the electrical gradient, if the electrical potential extracellularly was the same as the electrical potential intracellularly, okay, so the membrane voltage was 0, then you'd get a lot more movement of chloride in when you opened a chloride channel. Okay, so, you know, the electrical gradient does dampen the concentration gradient's attempts to get chloride to go in, but it doesn't stop it. Okay, you do still get chloride going in. Okay, right. At these excitatory synapses then, you'll be getting sodium currents coming into the dendritic spine. At these inhibitory synapses, you'll be getting chloride currents coming into the cytoplasm of the dendritic spine. Okay, and this then is now going to diffuse from the dendritic spine to the cytoplasm of the axon hillock. At least a little bit of it is going to make its way from where the dendritic spine was to the axon hillock. Okay, so the concept here then is that the dendrites of this neuron are covered in these dendritic spines. Okay, at any one moment you're going to have loads of the inhibitory synapses active. Okay, and they're all going to be causing chloride to come into the cytoplasm of the cell, and little bits of this chloride will be making its way to the axon hillock cytoplasm. Okay, and then you'll also have loads of excitatory inputs active at any one time. Those will be releasing glutamate, and they'll be activating sodium to come into the cytoplasm of the dendritic spines, and then little traces of this sodium will end up in the cytoplasm of the axon hillock. Okay, and then of course sodium and chloride are going to neutralize each other's effects because one is positive and one is negative. Okay, and then the axon hillock is only going to respond if one of those inputs overrides the other. So if you get much more sodium arriving here than chloride, then that obviously means that the excitatory input is bigger than the inhibitory input, and therefore that's going to induce it to fire an action potential. Okay, whereas when the amount of sodium arriving and the amount of chloride arriving is the same, then that obviously means that the inhibitory and excitatory inputs are matched, so it's not going to fire an action potential. Okay, so let's now talk about how, when the sodium arriving in the cytoplasm of the axon hillock beats the amount of chloride arriving in the cytoplasm of the axon hillock, how then does that actually activate an action potential? Okay, so now we're actually going to discuss then the initiation of an action potential. Okay, so there are two key voltage-gated ion channels in the process of an action potential. Again, they are voltage-gated sodium channels and voltage-gated potassium channels, and I'll start just by drawing out the voltage-gated sodium channels and the voltage-gated potassium channels, okay, because they're going to be so essential to understand. So we'll have the voltage-gated sodium channels here represented in green. Okay, so this is our voltage-gated sodium channel. Okay, and the abbreviation for voltage-gated sodium channel is VGNC. Okay, N here is for Na, the periodic table symbol for sodium. Okay, then here in blue we'll have our voltage-gated potassium channels, VGKCs. Okay, again that's the abbreviation for voltage-gated potassium channel using the periodic table symbol for potassium there. Okay, so the reason that dendrites can't fire action potentials, and then the axon hillock, and indeed the rest of the axon after the axon hillock, can fire action potentials, is because in the axon hillock and the axon you have lots of these voltage-gated ion channels, so loads of voltage-gated sodium channels and loads of voltage-gated potassium channels, whereas in the dendrites you just don't have enough of these, okay, to actually generate an action potential. So that's why the action potential can only be initiated at the axon hillock, not in the dendrites. Okay, right, so we have said that the action potential is going to be initiated in response to more sodium arriving in the axon hillock than chloride arriving there. Okay, so you're getting a net amount of positive charge arriving in the cytoplasm of the axon terminal. Okay, now, how do you activate voltage-gated ion channels? Again, I'm sorry, they're already drawn open, but in reality, if we're at negative 65 millivolts, these should be closed. Okay, I've drawn them open because, of course, they're going to open in the action potential, but imagine that they're closed at the moment. Okay, so you activate voltage-gated ion channels by depolarizing the electrical potential difference across the cell membrane. So when the electrical potential difference across the cell membrane is negative 65 millivolts, okay, these are going to be closed. Okay, if you want to activate an action potential, then you need to open these, basically. And we'll see exactly what an action potential is in a moment. But to get an action potential, you need to open these. Okay, how are you going to open them? Well, by depolarizing the electrical potential difference across the cell membrane. And that's exactly what the arrival of a net amount of positive charge into the cytoplasm of the axon hillock is going to do. Okay, right. So I'm going to draw a graph here, because graphs are actually very helpful here. Okay, so on the y-axis we will have the electrical potential difference across the cell membrane, and on the x-axis we'll have time. Okay, and this is the electrical potential difference across the cell membrane of the axon hillock. Okay, and it started off at this resting level of negative 65 millivolts down here. Okay, now let's say we get this period where we're getting more excitation into the dendritic spines of this neuron than inhibition, okay, and therefore we get this net amount of sodium arriving in the axon hillock cytoplasm, okay, compared to chloride. So we're now going to have a net amount of positive charge arriving in the cytoplasm of the axon hillock. Okay, so net amount of positive charge then. Okay, what is that going to do to the electrical potential difference across the cell membrane of the axon hillock? Well, I claim it's going to depolarize it. Now, why is it going to depolarize it? Well, another important law of physics is that where you stick positive charge, you raise the electrical potential, basically. Okay, we are bringing positive charge into the cytoplasm of the axon hillock. Okay, more positive charge. Okay, that's going to raise the electrical potential intracellularly. Okay, so we are now raising the electrical potential intracellularly because we're dumping this additional positive charge into the axon hillock cytoplasm. Okay, whilst the electrical potential extracellularly is going to remain roughly the same. Now, what is that going to do to the electrical potential difference across the cell membrane? Well, it's probably best seen on this picture here. We are now raising this number here. We're raising the electrical potential intracellularly here. Okay, so now the drop down from extracellular to intracellular, that's going to be a smaller drop, basically. It's going to be less negative. Okay, and when you make the electrical potential difference across the cell membrane less negative, that's called depolarization. So we are depolarizing the electrical potential difference across the axon hillock cell membrane by bringing in this net amount of positive charge into the cytoplasm of the axon hillock. Okay, so drawing this on our graph, we're going to go like this. Okay, now the axon hillock doesn't fire an action potential as soon as a bit of net positive charge arrives. This net positive charge that is arriving in the axon hillock has to be big enough, basically, to get an action potential actually to fire. Okay, if you only get a tiny amount of net positive charge, then that's only a tiny amount of net excitation, and that's not enough to make the neuron fire an action potential. Okay, you specifically need to get an amount of positive charge, net positive charge, coming into the axon hillock cytoplasm that can depolarize the electrical potential difference across the cell membrane of the axon hillock up to the threshold potential for the activation of the voltage-gated sodium and the voltage-gated potassium channels. So these voltage-gated ion channels, they have a certain electrical potential difference that they need the cell membrane to go up to if you're going to actually open them. Okay, and this electrical potential difference is called the threshold potential. Okay, so you need to get a large enough net positive charge coming into the cytoplasm of the axon hillock to depolarize the electrical potential difference across the cell membrane of the axon hillock up to threshold potential. Now, what actually is the threshold potential? Well, it's around negative 40 millivolts, basically. Okay, so you need to get enough positive charge coming in here to depolarize the electrical potential difference across the axon hillock cell membrane up to negative 40 millivolts, and then, if you manage to do that, then the axon hillock will initiate an action potential. Okay, so now what actually is an action potential? What is going to happen? Okay, right, so when you get the electrical potential difference across the cell membrane up to the threshold potential here, what's going to happen is the voltage-gated sodium channels and, in fact, the voltage-gated potassium channels are going to be activated to open. However, the voltage-gated sodium channels, they are incredibly quick. They open extremely quickly, whereas the voltage-gated potassium channels, they faff about a bit more. Okay, so even though they've been activated to open at the same time, these ones open ridiculously quickly, and these ones don't. They faff about, they remain closed whilst these ones have already opened. Okay, so in this first portion of the action potential, the important voltage-gated ion channel is the voltage-gated sodium channel. So these open almost instantly, basically, as soon as you get up to threshold potential. Okay, and I want to stress also that although I've only drawn one here, okay, in this patch of membrane you'll have a huge number of voltage-gated sodium channels, and they're all going to be doing this same behaviour. They're all going to now be opening. Okay, right. Now, when these voltage-gated sodium channels open, you've now opened a sodium channel in the cell membrane. When you open a sodium channel in the cell membrane, we know what happens, okay? There is a 12-fold concentration gradient of sodium favouring its movement into the cell. At the moment, the electrical potential is still lower intracellularly than it is extracellularly. Okay, by a lower degree, okay, it's only by negative 40 millivolts now, but it's still lower, okay, so initially both the concentration gradient and the electrical gradient across the cell membrane are going to favour the movement of sodium in, okay, so you're bringing in more sodium ions into the cell. Okay, now, when we bring in these sodium ions into the cytoplasm of the axon hillock, what then is that going to do to the electrical potential difference across the cell membrane of the axon hillock? Okay, well again it's going to alter it. Okay, because sodium is a positively charged ion and therefore is going to alter the electrical potentials of the areas that are involved. Okay, so we are bringing sodium into the intracellular compartment. Okay, and that's going to be raising the electrical potential intracellularly, because remember, where you dump positively charged ions, you raise the electrical potential. It's also actually going to be lowering the electrical potential extracellularly. Why? Because we got this sodium from somewhere. We had to take it from the extracellular compartment. So when we snatched the sodium from the extracellular compartment to dump it into the intracellular compartment, we were lowering the electrical potential extracellularly, because when the sodium was in the extracellular compartment, it was boosting the electrical potential extracellularly up. So when we snatched away from there, that causes the electrical potential extracellularly to go down. So once again, if I draw this basic picture here, if this is the electrical potential extracellularly and this is the electrical potential intracellularly, initially we had to step down by negative 40 millivolts. Now I'm saying the electrical potential extracellularly is going down, the electrical potential intracellularly is going up. So you can see that now the electrical potential difference is going to become less and less negative, basically. The amount you have to drop down from here to here is going to become less negative. So this graph ends up doing this, basically. And indeed it actually goes into the positive levels, where now the electrical potential intracellularly actually ends up higher than the electrical potential extracellularly. And when you go from extracellular to intracellular, you end up having to go up electrical potential, basically. Okay, right. So it goes up and up and up, basically. Okay, and you might think, but surely when we start getting positive electrical potential differences across the cell membrane, surely then we're going to stop getting sodium coming in. But remember, you've still got the concentration gradient. Okay, you've still got the 12-fold concentration gradient favouring the movement of sodium into the cytoplasm of the cell. Okay, so even though the electrical gradient has switched now, and now sodium will want to go out because the extracellular compartment has the lower electrical potential now, okay, the concentration gradient is still driving the movement of sodium into the cell, so you still actually get the movement of sodium into the cell. So this is the upstroke of the action potential. Now, you get up to an electrical potential difference across the cell membrane of around plus 40 millivolts. So the intracellular compartment's electrical potential is now greater than the electrical potential of the extracellular compartment by 40 millivolts, basically. If you move from here to here, the electrical potential goes up by 40 millivolts. Okay, and then what happens is you stop getting sodium coming into the cell. Okay, and it's not to do, repeat, it's not to do with the fact that suddenly that's too high an electrical potential difference across the cell membrane for sodium to continue coming in. Instead, it's because the voltage-gated sodium channels actually close, they inactivate, okay? So they open very, very fastly, basically. As soon as you get to threshold potential, they open, okay? But they also inactivate within 1 or 2 milliseconds of opening, basically. And that's what we're seeing now. We're seeing the voltage-gated sodium channels inactivating, okay? And therefore, the sodium currents coming into the cell stop, so you're not going to get any further depolarization beyond plus 40 millivolts. Okay, and that mechanism of inactivation, we're going to be studying that more in detail later. Okay, so it's not just the channels going back to being closed, they're going into a different state from being closed, basically. Okay, because after all, we're still depolarized at the threshold potential, so the voltage-gated sodium channels should still be activated to open. Okay, why have they now closed? Well, it's a different mechanism, basically, and we will study that in more detail later. Okay, right, so I think we'll have a break here, okay, and we'll continue this discussion of action potentials in the next video.